All right, so last lecture we talked, that's not how I do that. Last lecture we talked about Buckingham Pi Theorem. We talked about how it can be used to greatly simplify modeling a physical phenomenon. We gave the example of the ball in air, trying to calculate the drag force, and how there's like tens of thousands of experiments you'd have to do to just do a mediocre job of experimentally characterizing the system. Whereas if you use Buckingham Pi Theorem and you put the drag coefficient dimensionless group in terms of a function of the Reynolds number, you can then do one series of experiments where you just vary the Reynolds number and solve for the drag coefficient and completely characterize the system, which allows you to essentially solve for this g. This g is this plot here of this curve, right? So it can be used to greatly simplify the modeling of physical phenomenon, and even if we don't know g, if we haven't done a whole bunch of experiments before, we can just do one experiment. If we know that what our prototype conditions are going to be like, we can match the pi 2, pi 3, pi 4 for our model to the pi 2, pi 3, pi 4, or pi p, whatever, of our model. Or sorry, we can match the pi 2 through pi p of our model to the pi 2 through pi p of our prototype. Then we know our pi 1s have to be equal to each other, and for our model experiment, we will calculate or measure pi 1 and set that equal to pi 1 of our prototype, and hopefully there's only one thing we don't know about our prototype. So this might be the drag on a giant ball that we can't possibly do an experiment for, but we want to be able to calculate it. We do an experiment on a basketball-sized ball, and we know all of the things like the density, the velocity, the diameter of all of our things. The only thing we don't know is the force on our prototype, the force on our gigantic ball. And as long as we matched our Reynolds number for our model and our prototype, which means we have to match our Reynolds number for our model and our prototype, then we know that these two parameters are equal and we can solve for FP. So that's super useful. That's called similarity. Similarity is matching all of these pi groups. And we'll talk a little bit more about that later. But today we're going to talk about how we find these pi groups. So, step one to finding these pi groups, well, before I do that, we should always say that you can always use something called inspection. Inspection is just basically winging it. For simpler problems, you can actually just look at and if you have a lot of experience with this, you can actually just look at the dimensionless groups and you can say, you look at the physical variables and be like, oh, I can see a Reynolds number coming out of this. It's usually a good bet. Reynolds number is always there. You can use inspection, like I said. But I wouldn't recommend it on an exam because the method I'm about to show you doesn't take long, but it virtually guarantees that you're going to get it right. So, first, step one, write down all of the parameters involved with units. Physical variables with units. Right? And I like to do this not with the actual units like seconds, meters, kilograms. I like to do it with the general units on them. So let's write this down. So let's do again our ball in air. So we have a velocity, we have a density and a viscosity, we have a diameter d, and we're trying to measure the drag force on this object. So we have 5 things we have to write down. Let's write those down. We have an FD, we have a density, we have a velocity at infinity, right? From far away. Let's call that V infinity. We have a diameter and we have a viscosity. So we're going to draw a line there, and then now we're going to write down the physical dimensions that are used in each of these things. We'll do the easy one first. Diameter is just a length. Density is just a mass per length cubed. Velocity at infinity is just a length per time. Viscosity is a little bit harder. It's a mass per length time. And the force is a mass length per time squared. Great. And then once you've done this, we write down n is equal to 5 because we have 1, 2, 3, 4, 5 physical variables. And we move on to step 2. Step 2 is figure out the number of pi groups. All right, so that's pretty easy. We count up the number of physical dimensions that we have here. We have mass, length, and time. We do not have charge or temperature, so we only have 3 primary dimensions. So k is equal to 3 primary dimensions. And n minus k is equal to 5 minus 3 is equal to 2. So again, we're doing the same problem over and over again, but we expect to have 2 pi groups, which we knew, but now it's, good to have confirmation of that. Step 3, choose repeating parameters, i.e. your building blocks. Your building blocks. All right, so repeating parameters are called repeating parameters because they'll show up in all of your pi groups. Well, they can show up in all of your pi groups. We have some rules for choosing these repeating parameters. So what we're choosing basically is we're choosing our physical variables. We're choosing among them, and we're going to choose our building blocks for our future pi groups amongst our physical variables here. Our rule number 1 is we must include all dimensions. So we can't just pick diameter. Well, hold on here. Actually, this isn't a great example because no matter any 3 that we pick, we'll have to do. Oh, by the way, yeah. So we must include all dimensions. 2 must be dimensionally unique. So in other words, this one basically says we must have mass, length, and time. This one says we can't choose, for example, a diameter and a radius, because those both have length and length. They're not dimensionally unique, so you can't choose dimension diameter, radius. 3, can't be powers of each other. So in other words, you can't choose diameter and area because that is length and length squared. Which really goes on to say that they're not dimensionally unique, honestly, because they're just powers of each other. Great. So we need to pick. We're going to have 2 pi groups, and we're going to build each of these 2 pi groups around 2 of our physical variables, and the rest become our repeating parameters. So we have that means we need 3 repeating parameters. Note this has to be. We need k repeating parameters. Okay, so we need 3 repeating parameters, and so I'm going to choose for this example, mu, d, and rho. Okay? We're going to pause here for a second, and you're going to probably ask me, like, well, there are lots of options which meet these requirements, particularly for here. Like, I could choose v, d, and mu, f. I could choose f, rho, v. You know, there's tons of options. And yeah, it's true. And every different combination of repeating parameters you pick will result in different pi groups. And just a heads up, some of those pi groups are going to be meaningless. Some of them are going to be not that meaningful, and some of them are going to be just perfect, right? They're going to be super meaningful. How do you know the difference? Experience and trial and error, right? So in some of these problems, people would try over and over different groups of repeating parameters. In other ones, maybe you know a dimensionless group that actually characterizes your data really well, and you can seek it out, right? So that's experience. So experience helps a lot. So either trial and error or experience. We will always tell you which repeating parameters to use on an exam, because we don't want you hunting around on an exam. All right, so step 5. Apparently we're going to skip one here. Step 4, I mean. Step 4. We're going to write out the pi groups with exponents. Okay? And so, write out pi groups with exponents. And so what we know is that our pi 1, for example, is going to be equal to our force times, so we're using this physical variable, and we're going to cancel out all of its units using our repeating parameters. So it's going to be multiplied by rho, diameter, and mu, and we're going to raise these to a power, each one of these to a power, a, b, and c, and we're going to solve for a, b, and c such that when rho is raised to a, diameter is raised to b, and the viscosity is raised to c, they cancel out all the units in our force F. Okay, so if we write out now our fundamental units, we say that force has mass length per time squared, and then we multiply that by a mass per length cubed to the a times a diameter, a length, to the b times a mass per length time to the c. And all that has to equal 0 because all of these things have to cancel out. How do we ensure that they cancel out? Well, we know that at the end of this, the sum of all of the exponents on these masses, all of the exponents on the lengths, and all the exponents on the times have to equal 0 when they sum together. Because remember, exponents on top of a fraction are positive and exponents on the bottom are negative. So, for example, this is a t to the negative 2. Down here on the bottom, that's an L to the positive 1 and an M to the positive 1. So what we can do is we can actually set up a system of equations that correspond to each of our physical dimensions, and where the only unknowns are these A, B, and C, and we can solve for A, B, and C. So let's do it. Let's do mass first. Mass. I'm going to write this in a little different color since it's getting a little tedious here. So let's do mass. Mass, we have, obviously everything has to equal 0. 0 is equal to, we have a m on the top, so that's a 1 plus, and now we're going to add each of the m's in each one of these terms. So we have a, it's 1m times a. We have 0 times b. I write them out even though they're there. So it's 0 times b plus 1 times c. And that's it. That's done for m. Now let's do t. Let's do l. We'll do l, and I'll have you guys do t. So we have ml. So l is going to be 0, always equal to 0. Our l is on top here, so it's a 1 plus Now that's a L to the negative 3 raised to the A, so it's L to the negative 3A. So we're going to put a negative 3A here. Plus 0B. There's no, oh, never mind. Eesh. That was a mistake. That's a 1B. To the 1B. So we have just an L here on top. And then we have a L on the bottom, so that's negative 1 to the C, so it's negative 1C. L to the negative 1C. Plus negative C. Now I'll let you guys do time. I want you to pause this and go through and follow that pattern and figure out what the time equation is. This is actually probably the easiest one. Pause the video, do it, and then unpause it. Okay, I'm going to assume you paused it. We have 0, because it always has to equal 0, because all of the units have to cancel out, is equal to, we have a negative 2 on the bottom. Excuse me. We have nothing at A, so plus 0A, plus we have nothing for B, plus 0B, and then we have a minus 1T to the C, so it's a minus 1C. So usually, if we're lucky, solving the system of equations ends up being fairly easy, because we can start with something like C here, and we can say, oh, C has to equal negative 2. Awesome. Once we know negative 2, we can plug in C into, let's say, the top here, and we can say, all right, well, if C equals negative 2, then if this is negative 2, A has to equal 1, positive 1. And if we plug 1 in here and a negative 2 here, we have negative 3 plus 2 gives us negative 1. That means B is equal to negative 1 plus 1 is 0. Oh, B is equal to 0. Awesome. So our pi 1 then, we can just write out by raising each one of these physical variables to the exponents that we just solved for. So pi 1 is equal to F times rho divided by B to the 0, but C to the negative 2. So mu squared on the bottom. All right. And now we can do the same thing for pi 2. So pi 2 is equal to, we're going to use our other variable we haven't used. So we did F first, now we're going to use V. So we have our velocity times rho to the A times D to the B mu to the C is equal to, not mass, length per time times mass per length cubed to the A, length to the B times mass over length time to the C, and all that has to equal 0. And now we go through and we do exactly the same thing as before. We do a system of equations and we solve for the values that satisfy that system of equations. So I'm going to let you do that now. I'm going to pause this video and I'm going to let you do it. And if you get stuck, you can watch the video until you get unstuck, but then pause it the second you get unstuck and kind of finish the video as you go along. Okay, I'm going to assume you paused it. Great. So mass, we're going to do mass first. We have 0 because all these have to cancel out and equal 0 is equal to, and we have nothing in the front here, so we have 0 plus A plus 0B plus 1C. For our length, we have 0 is equal to, we have a 1 on top, so that's an L on top, so that's L to the 1. Oops, I'm writing the things I'm saying. We have a 1 plus, and now we have an L to the negative 3A, so it'd be a negative 3A, plus B plus negative C. And now at time, we have 0 is equal to, we have a T on the bottom, so we have a negative 1. We have nothing for A. We have nothing for B, 0B. And we have negative 1 for C, so we're going to have a negative C here. Now you'll notice actually that everything here stays the same. we use this same over and over and over again. So you can save some time and just copy those down. But it's good to do it twice in a row. All right. So now if we were to figure out what these values of a, b, and c that satisfy our system of equations, we can find out that c is equal to -1, a is equal to 1, and b is equal to 1. All right, so if we write this out, we get that our pi 2 is equal to our velocity times a, rho, okay, so rho's on top, diameter's on top, divided by our viscosity, which we should start recognizing. You should start being able to say what that is. It is the Reynolds number, right? So you'll notice this is not the dimensionless group that we talked about before. This is not our drag coefficient, right? And the reason is because we chose a different set of repeating parameters than we would need to choose in order for the drag coefficient to come out. And so what this is telling us is that our pi 1 is equal to the ratio of our force times our mass. Our force divided by our force times our density divided by our viscosity squared. And we could probably find some meaning about this, but it's unlikely, right? And it's not very useful to us. This pi group is not very useful because, remember, density and mu are linked by the material properties of whatever fluid or fluid that our system is in. So if we are in like water, this is going to be two options here, and that won't change very much based on like temperature. With air, we have some more flexibility, but it's still very hard to change them. So this isn't a very useful pi 1, right? And we'll show what happens if we choose different repeating parameters next. We're going to practice this again. So we have these two pi groups, and what does Buckingham Pi Theorem tell us? Buckingham Pi Theorem tells us that pi 1 is equal to some unknown function of pi 2. Or we could write this as f rho over mu squared is equal to some unknown function of rho v d over mu. And if we really wanted to, well, actually we can rewrite this again if we want. Hold on. This is equal to the Reynolds number. And if we really wanted to now, we could do a whole bunch of experiments where we change the Reynolds number, and there's lots of ways to change the Reynolds number. We could change the fluid that it's in, we could change the velocity, we could change the diameter. We only have to change one of those in order to change the Reynolds number, and that's fine. But we change the Reynolds number and then measure the ratio of the force times the density divided by mu squared, and we could develop a plot just like with our drag coefficient. F rho over mu squared is equal or as relative to rho v d over mu, which remember is equal to the Reynolds number. I have no idea what this plot would look like. I would have to guess that at low Reynolds numbers we have a lower force, and then as we get to higher ones we have a higher force. That's the opposite of what I drew, isn't it? If I had to guess, it's going to go something like this. But I don't know. I've never seen this plot before because it's not useful. Nobody's ever done these experiments and nobody has ever plotted that. So let's choose some different repeating parameters and see what happens. Let's do this practice again, only choosing rho as a repeating parameter, v as a repeating parameter, and d as a repeating parameter. So first, before we move on, let's check and make sure this meets all of our requirements. Do we have all of our physical dimensions represented? We have mass, length, and time. Good. We have all of them. Are all of our repeating parameters, all of our building blocks, are they dimensionally unique? And yeah, they are. We have length over time, and mass per length cubed. So that is unique. And finally, are they any of them powers of the other? And the answer is no. We have diameter, velocity, and rho. So they're good. They're unique enough that we can use them now to build our pi groups. So let's do that. All right, so F1, our pi 1, is going to be equal to, let's start again with our FD. And it is convention to almost always there will be one of the physical variables that you care about in your system that you're trying to measure or predict, right? So in our system here, we're trying to predict our FD. We're trying to model our FD. So it's convention to build pi 1 around FD. Okay? So pi 1 is equal to F times rho to the A, V to the B, and D to the C, which is equal to mass length per time squared times mass per length cubed to the A. We have a I did it again. We have a length per time to the B and a length to the C. All right, so I want you guys to build our system of equations. Go ahead and build our system of equations. Remember, you have to start with mass. Well, you don't have to start with mass, but I usually just start with mass. And pause the video and go ahead and do that. Do some real good engaged learning here. Don't just copy down what I'm writing. All right, I'm going to assume you came back. So we have mass. We have 0. Always has to equal 0 because we're trying to get all the units to cancel out. And we have a single m on top, so it'll be 1 plus a, because we just have a m on top, so it's m to the 1 times a, plus 0 plus 0, b plus 0c. Well, good. We know a is going to be easy to solve for. Let's do length. 0 is equal to, we have a length on top, so we're going to have a positive 1, plus we have a l to the negative 3 times a, so that's a negative 3a. We have a l on top, so that's l to the 1b, so that's a 1b, plus l to the 1c, plus c. And now time, we have 0 is equal to negative 2, because we have a negative 2 on bottom, so negative 2, plus 0a, plus negative b. We have a t to the negative 1b. And we have no t here, so it's a plus a 0c. Awesome. So actually, both our b and our a are going to be easy to solve for. I'm going to let you guys do that real quick. Pause the video, or hopefully you've already done it. And if not, great. All right, let's do it. So we know that our a is going to equal negative 1. We know that our b has to equal negative 2 from this equation here. And we've plugged both of these into here. We find out that our c is equal to negative 2. Awesome. So let's write this out. We have pi 1 is equal to f times, all right, well, our rho is to the negative 1, so it's divided by rho. Our velocity is to the negative 2, so we have v squared. Uh-oh, this is starting to look like the drag coefficient. And our diameter is raised to the negative 2, so that would be d squared down here. And that is our drag coefficient, which is comforting. It's comforting. That's equal to our CD. I'm going to let you do pi 2 again, knowing what pi 2 is going to end up being, because we have a viscosity times a rho to the A, V to the B, D to the C. Anytime we have a rho, V, D, and mu together, we know that there's going to end up being the Reynolds number, right? In some form. So I'm going to let you do this. I'm going to let you write out the equation here to set it up. And then I'm going to let you do the system of equations and solve for A, B, and C, knowing what A, B, and C have to be. Although, just a heads up before you start, it's not going to be Reynolds number. It's going to be equal to Reynolds number to the negative 1. Okay, go ahead and do it, and then come back, or unpause, or whatever. All right, so we have, for our equation here, we have mass over length and time times m over L cubed to the A, L over T to the B times L to the C. And for our system of equations, then we get mass. If we do mass, we find out that 0, the colon, 0 is equal to, we have mass on top, so it's 1 plus 1 to the A plus 0 to the B plus 0C. Length, 0 is equal to, we have L on bottom here, so we have a negative 1 plus negative 3 to the A, so negative 3A, plus 1 L to the 1B, so that's A plus B, plus L to the C, which is C, 1C. And then time, we have 0 is equal to, T is on the bottom, so negative 1T, plus 0A minus B plus C. Again, remember, these are just, everything from here over is repeating from here. So if you're on an exam and pressed for time, you can just copy these down, but you got to make sure you did them right. So if you're on an exam and you're doing this and you see, or doing homework and you see that they're different, that's also a sign that you did something wrong. And you should go back and check your work. Okay, so we can solve for these variables, and hopefully you've done that already. And when we solve for them, we see that B is equal to negative 1, A is equal to negative 1, plug both of those in and solve for C, and we find that C is equal to negative 1. So when we write out our pi group, we get that pi 2 is equal to mu divided by rho v d, which is just equal to Reynolds number to the negative 1. And so, remember that our Buckingham Pi Theorem then tells us that our pi 1 is equal to some unknown function of pi 2. So that our pi 1 is equal, sorry, I was supposed to write out our actual pi 1 here. Our f over rho v squared d squared is equal to some unknown function of mu over rho v d, or it's equal to some unknown function of the Reynolds number to the negative 1. Now, that's not what we wrote up here. You'll notice up here, previously in our notes, we've got to keep going, keep going, keep going. Maybe I skipped over it. Now, up here we wrote that our drag coefficient is equal to a function of our Reynolds number, but we put our rho vd on top. And the reason we did that is we don't know what this function looks like. This function could be anything. It could even be a boat. Its function could be anything. So we can add, if we want to, a inverse, well, 1 over to this function, and we can just say that, and we can call it something new. You want to call it h? H works. So we can say that f is equal to rho v squared d squared times h to the h of Reynolds number, like that, where this is just equal to g of Reynolds number to the negative 1 to the negative 1, right? So we can play around with it and massage it so that it looks a way that we're familiar with, is really what it is. And that's okay, because if we don't already know the function, then flipping Reynolds number is just going to flip our function, right? Cool. So we're going to finish this lecture with a little bit of a discussion of, I know it's going a little long, but this won't take much longer, what the meaning of dimensionless groups like Reynolds number is. So if we have our Reynolds number is equal to a rho v d over mu. We can rewrite that as equal to a rho times v over a mu over d, right? And this top part is a density times a velocity, right? That's inertia, right? Mass times velocity is inertia. It's momentum. And the bottom part is a mu divided by L, mu divided by L, which is a measure of our viscous forces, right? Because remember, what we said is that if we have a very small d, our viscous forces go up. And if we have a big mu, our viscous forces go up. If we have a viscous fluid, we're going to have a high viscosity. So this is a measure of our viscous forces. So large Reynolds numbers suggest that inertia, if Reynolds number is high, inertia dominates. And low Reynolds numbers suggest that viscous forces dominate our flow. And this is why Reynolds number is so dang useful for characterizing flows and why we use it so often, and why if you're on an interview and you're stuck, you're like, what's the Reynolds number range? People are going to be like, this guy, he gets fluids. It turns out that for fluid flow, really slow fluid flow, up to about a third of the speed of sound, knowing the ratio of inertial to viscous forces in a flow tells you a lot about how that flow is going to behave. The character of that flow, not the specifics about what the velocity is here or the shear stress is there, but it will tell you the character of the flow. How turbulent is it? How laminar is it? Things like that. And that's super useful stuff to know in terms of design, right? Or just engineering in general. Another really useful dimensionless parameter in fluids is the Euler number. Euler number. It is equal to pressure divided by 1/2 rho v squared. So this is equal to the ratio of pressure energy to, hopefully you can get this actually. I'm going to pause and let you write it down, but this should look dang familiar. Yep, kinetic energy. Kinetic energy. So that's pressure to kinetic energy, dimensionless parameter. We also have something called a Freud number. Is equal to our velocity divided by our square root of our gravity times the length of our object, some characteristic length. So, if you can guess, imagine if we added a rho to both of these. What would the top be and what would the bottom be? Well, the top would be inertia, again, divided by gravitational flow. And actually, if we really wanted to write this out, we would write it as rho v squared square rooted all over the square root of rho GL. And then it's a little bit more clear too. It's not so much inertia as kinetic energy over potential energy. Right? So we have a ratio of kinetic energy over potential energy, and this is actually super useful for long container ships. So long container ships or oil tankers or any long ship will build up what's called a bow wave, and that bow wave will be in front of the ship, and it comes up and it comes down, and it goes like, well, I'm exaggerating it comes back, and it is the fundamental thing that limits the speed of one of these ships, right? Because it makes the ship seem like it's constantly going uphill if you try to outrun this wave. And it turns out that the longer a ship is, the longer this wave has to be in order for that ship to have to overcome it, so the ship can go faster, right? Which is why, one of the reasons why ships keep getting longer and longer and longer is so that they can go faster and faster and faster more efficiently. Also, by the way, that little bow, bulb, it was an innovation to try to reduce the bow wave, and it actually does a decent job of it. But it's still fundamentally there. It just moves the limit as opposed to eliminating it. And so we fundamentally want to increase the length of container ships in order to get them to be more efficient and go at higher velocities. Although you'll notice that it's the square root of L over V. So if we were to plot the maximum velocity of a container ship versus the length, if this is our V and this is our L, we're going to find out that we get something like this, right? So you get diminishing returns the larger and longer your ship gets. So you have to get, in order to double your velocity, you have to go 4 times your ship length. So once you're in the hundreds of meters, you're never going to, well, maybe thousands of meters now. Is there a 1,000-meter long ship? I think there are 1,000-meter long ships. You're not going to go to a 4-kilometer long ship to double your velocity. Yeah. Cool. Another dimensionless parameter is our Mach number, which you guys should know is equal to our velocity of our object or fluid divided by the speed of sound. and this is our speed. Speed of something, object or fluid, everything's relative. That one you're familiar with. It's a measure of when compressibility effects become important. And finally, we have a Weber number, which is equal to rho v squared L squared over sigma. And it's a ratio of kinetic energy to, this is, by the way, the surface tension coefficient. Ratio of kinetic energy to surface tension potential. So you can actually, you can look for videos of this, but you can actually see surface tension like pull a string into a perfect circle when it's sitting on a tub of water or something like that. And that is exactly what we're talking about in terms of tension potential. The system is lowering its energy because it has surface tension potential there. So it's the ratio of kinetic energy to surface tension potential in a system. So it's whether or not surface tension forces become important. And as you'll notice, L's on top. So as L gets smaller, kinetic energy becomes less important and surface tension becomes more important. Same is true with velocity, although L ends up dominating that system there. So in like microscale flow, which is something my lab deals with all the time, kinetic energy is relatively unimportant because we're dealing with microns length scales here, or even millimeters, which is at the best case scenario 1 times 10 to the negative third squared, which is 1 times 10 to the negative 6, and we're rarely dealing with velocities more than a meter per second. So this is, the top is very small and the bottom doesn't. So kinetic energy is completely negligible and surface tension becomes very important. All right. The next lecture we will start practicing this stuff.